Watch a modern automated production line, and you will see heavy steel moving at terrifying speeds. An arm swings across a chassis, drops to a specific millimeter coordinate, and stops cold. To make that motion happen without tearing the machine apart, an industrial controller coordinates multiple servo motors simultaneously. It must send out positioning data, read the feedback, and calculate the next move with cycle times under 1 single millisecond. When we need to move data in an office, we use standard Ethernet. The universal RJ45 cable connects servers, computers, and printers worldwide. But plug that standard Ethernet into a factory floor, and the entire production line will crash. The problem lies in the original Ethernet protocol itself, specifically a mechanism called CSMA/CD. CSMA/CD stands for Carrier Sense Multiple Access with Collision Detection. It is probabilistic. A node listens to the wire. If it sounds clear, it broadcasts. But if two nodes broadcast at the exact same moment, their packets collide. The data is destroyed. Both nodes pause for a random fraction of a second, and they try again. In an office IT network, these routing delays and retransmissions are harmless. A 10-millisecond delay to reload a spreadsheet goes completely unnoticed by a human sitting at a desk. On a factory floor, 10 milliseconds of silence means a multi-ton robotic arm continues along its trajectory without an updated stopping coordinate. It will smash through a workpiece and destroy the tooling. The IT environment tolerates probability. Physical manufacturing requires absolute certainty. That requirement for absolute certainty is called determinism. It is the mathematical guarantee that a specific packet of data will arrive at a specific node exactly when expected, every single time. We used to achieve precision mechanically. In early assembly lines, synchronization was handled by physical linkages, drive shafts, and gears turning at fixed ratios. Today, those mechanical linkages have been replaced by digital networks. Dozens of independent motors must act as if they are physically geared together. Early programmable logic controllers achieved this by using serial master-slave protocols, like RS-485 Modbus RTU. The controller acted as a strict conductor, speaking to one device at a time. These serial networks were highly deterministic, but severely limited by their polling cycle. The master had to ask device 1 for its status, wait for an answer, ask device 2, and so on. As factories added more sensors, this sequential process choked on the data volume. Automation engineers faced a bottleneck. They needed the massive bandwidth of modern Ethernet, but they could not surrender the strict, predictable cycle times of legacy serial connections. Getting true determinism at Ethernet speeds required engineers to rewrite how data physically interacts with silicon. The first attempt to solve this problem gave us protocols like Ethernet IP. It acts as a baseline industrial solution by adopting standard IT networking rules for automation. Ethernet IP relies on the standard OSI network model. It wraps automation commands inside standard TCP, UDP, and IP software layers. As the command travels from the controller down through the software stack, it accumulates routing headers at each layer until it finally hits the physical wire. When that packet reaches a destination node, like a motor drive, the device's internal CPU must use software to unpack those layers. It reads the IP header, strips it, reads the TCP header, strips it, and eventually finds the command data. Even though systems use the Common Industrial Protocol to optimize messaging on top of this stack, the underlying TCP/IP unpacking process is handled by a software processor. Software execution times vary based on CPU load. That makes it inherently non-deterministic. Engineers can simulate determinism using highly managed switches to prioritize traffic and isolate the control network from the office network. But for isochronous real-time motion control, where multiple servo axes must adjust their torque simultaneously, this software-based execution remains too slow. If a device relies on a software CPU to process routing headers, it cannot achieve the microsecond synchronization required for hard real-time motion. This software bottleneck drove the creation of advanced industrial Ethernet protocols, engineered specifically for high-speed motion control, EtherCAT, Profinet IRT, and Circos 3. Their architectural leap is simple. For critical process data, they completely abandon the TCP, UDP, IP software stack. Instead of relying on a processor to route software, they subvert the MAC layer. They bake the protocol execution directly into specialized hardware ASICs, silicon chips hardwired to handle the data instantly. This enables on-the-fly processing. A single standard IEEE 802.3 Ethernet frame is sent down the wire. When that frame reaches a slave node, it does not stop. It is not buffered, and it is never unpacked by a software CPU. The frame physically passes right through the node. As the data streams past, the MAC layer hardware extracts the specific command data addressed to that drive, and concurrently injects the drive's current feedback data into the exact same moving frame. By extracting and inserting data directly at the hardware level, processing latency at each node drops to virtually zero. This pushes cycle times down to 31.25 microseconds. They treat the Ethernet frame as a high-speed conveyor belt manipulated directly by hardware. By eliminating software latency entirely, they achieve mathematically perfect synchronization. Because these protocols process data physically as it moves down the wire, the physical layout of the cables, the topology, becomes a critical engineering constraint. Standard IT networks use a centralized star topology. Every computer wires back to a central switch, which routes the traffic as needed. This diagram illustrates the shift. An industrial network moves away from that top star topology and relies heavily on the ring or line topologies shown below. A line topology forces the continuous Ethernet frame to daisy chain from one servo drive directly into the next. The physical layout guarantees the sequence and timing of the data flow. Moving the routing burden off centralized switches and onto the individual nodes allows for massive scalability. A single EtherCAT network can support up to 65,535 nodes, all reacting in predictable unison. In the world of industrial Ethernet, the physical cabling architecture functions as an active component of the network's deterministic performance. A modern automated factory relies on a strict hierarchy. A human operator inputs a command at the graphical HMI, which relays it down to the programmable logic controller. From that PLC nexus, the commands travel down a deterministic, hardwired line directly to high-voltage industrial drives and real-time sensors. Achieving this level of physical control requires abandoning the probabilistic software routing that powers the global internet. Moving data is about flexible communication. Moving heavy machinery is about rigid synchronization. The flashing link LED on an industrial drive represents a microsecond perfect hardware-level orchestration that makes modern physical automation possible.
Thanks for watching and grow every day with just a bit of information. Like, share, and subscribe for more content and learning.